In this video I would like to give a brief background about myself. Firstly, I studied electronic engineering. I did my undergraduate degree in electronic engineering, and then I completed my master's degree in applied mathematical sciences. I went to Scotland and I graduated from Heriot-Watt University with merit. And after that I went to Glasgow, and more precisely to University of Strathclyde, and I obtained my PhD in mathematics. The main topic of my thesis is, the title is the following one: Scalable Domain Decomposition Methods for Time Harmonic Problems. I studied the behavior of Schwarz algorithms, which were used in the time harmonic problems. So Schwarz algorithms for time harmonic problems. Of course, time harmonic problems, mostly we pay attention to Maxwell's equations. These are the Maxwell's equations, these coupled PDEs, and more precisely I studied the scalar Helmholtz equation with absorption, which is of the following form: plus the boundary conditions and also I studied the shifted Laplace problem with a complex coefficient of this form, where you have this complex coefficient there plus boundary conditions. Now the Schwarz methods were devised by Hermann Schwarz, of course. Let's imagine that we have to solve a problem in this bounded region omega with a Lipschitz boundary. Let's assume that we have this problem and u is equal to 0 on the boundary of omega. Then the Schwarz algorithm says the following: that we can decompose this problem into two local subproblems, omega 1 and omega 2. This is gamma 1 and gamma 2 are the two interfaces, so we can write the algorithm like this. and we have the external boundary. The external boundary condition. So in the first subdomain we have this local boundary value problem, and in the second subdomain we can write the other boundary value problem in omega 2. So this is called the alternating Schwarz method. And L is let's say an operator, it could be an elliptic operator. Therefore we have generated this problem, we have decoupled this problem into two coupled subproblems, and we solve in the first subdomain, we go to the second subdomain, we have an initial guess, we go to the second subdomain, we go back and forth, and we obtain the solution sequentially. We go from one subdomain to the other, back and forth, until we reach the convergence of the method. Of course, there is also the parallel Schwarz method. And there is a proposition to modify the interface condition at gamma 2 so that we rewrite the algorithm like this. And in the second subdomain we have the other local boundary value problem, and we have that u2 of n is the iteration that we have, and the iterate is u1 of n minus 1, the previous iterate at gamma 2, and u2 of n is equal to 0 on the external boundary. Therefore, this method enables us to have a parallel algorithm. We have a the parallel Schwarz algorithm, where we need two initial guesses at the two interfaces gamma 1 and gamma 2, and we solve in parallel and we obtain the solutions. We solve at the same time and we obtain the solutions, and we update until we reach the convergence of the scheme. Therefore, these methods are very useful in order to break the computational cost efficiently, and in order to alleviate the expensive calculations that could be done in one subdomain. So doing in one subdomain calculation could be expensive, therefore you break it into smaller and smaller problems. You solve each problem in each subdomain and you glue all the solutions together. This is the idea, and this can be generalized to more than two subdomains. There is already literature available and plenty of research findings. Of course, there is a variant of this algorithm where you can modify the interface conditions. You can use Robin interface conditions there to make the algorithm more efficient and to get better convergence properties. And there is a whole research activity dedicated to the optimized Schwarz methods with plenty of research findings. So this was a brief introduction to what I have, to who I am and to what I have achieved the previous years. It's just to have an idea and to let you know.